Now let's look at an example of bi-infinite interval. It means we have an integral from negative infinity to positive infinity. So let's look at an example like this kind. From negative infinity to positive infinity, a rather good integrand, 1 plus x squared dx. Okay. Now, by definition, this can be split into two improper integrals, one from 0 to infinity and 1 over 1 plus x squared dx, and plus from negative infinity to 0 and 1 over 1 plus x squared dx. Of course, we can also split this integral from, say, 1 to infinity and negative infinity to 1, but 0 is the most convenient point. Soon we will see. So now we have two limits to calculate. Here, the first one is the limit from, let me still use capital A. Our textbook used T, doesn't really matter. A going to infinity, and from 0 to A, and 1 over 1 plus x squared dx. Now for the second one, we can use a different symbol over here. We can use b going to negative infinity, and then this is going to be b to 0 and 1 plus x squared dx. Okay. We have two limits to calculate. And then the first one, we have limit a is going to infinity, and integrate 1 over 1 plus x squared is easy because it's a formula. That what we have is arctangent. Arctangent x, and going from 0 to capital A. And the second one is also an arctangent. The limit b is going to negative infinity and b to 0 and 1 over 1 plus x squared dx. We can do it again. The first one over here, we have arctangent a, so the limit a going to infinity, arctangent a minus arctangent 0, right? And the second one, we could have done it a little earlier, but it's the limit a going to b going to negative infinity, and what we have is arctangent 0 and minus arctangent b. That's what we have. Now, recall the graph of arctangent. Arctangent looks like this. Right here is pi over 2, and here we have pi over 2 negative. So we see that the limit, the first limit over here is pi over 2 and minus 0. Arctangent 0 is 0. And second one over here, we have 0 and minus negative pi over 2, right? And that's going to be equal to pi over 2 plus pi over 2, and that's going to be pi. Now, remember, the meaning, the geometric meaning of a definite integral is the area beneath the curve. So let's look at what kind of function we have. We have a function called 1 over 1 plus x squared. We can sketch it without using even calculus or anything. So when x is 0, this is going to be 1. When x is large, it's going to get a small value, and everything is smooth. So looks like this one. So what we have for this function is that inside over here, we have the area over here is equal to pi. Okay. All right, let's look at another example. The following example is very, very important because it has a parameter p inside. It tells us when we have the limit finite or infinite. So we have a function x to the power 1 to the x 1 over x to the power p, and p is positive. Okay, and we noticed that if we want to have an area under curve, we must have a function over here decreasing, or at least the area is going to be small. So look at this function. From 1 to infinity, it looks like this: 1 over x to the power p. If p is greater than 0, we know the following thing. If x is going to infinity, 1 over x to the power p is equal to 0, and it's decreasing. So we are looking at this area. You may wonder why we don't look at the area between 0 and positive infinity, because then we have trouble, because when x is small, this function is large. That's a different kind of improper integral we will discuss in our third segment of the lecture. So let's look at what kind of value we're going to have if we integrate from 1 to infinity and 1 over x to the power p and dx. So this is a limit. Let's say use t. T is going to infinity, and from 1 to t, and then we have x to the negative power p dx. So this is the limit. T is going to infinity, and we have 1 over negative p plus 1, and x to the negative p plus 1. And then we plug in t and 1. Okay. Now, here we must separate the cases, because p cannot be equal to 1. Otherwise, we have a 0 in the denominator. So after you plug it in, then we have limit t is approaching infinity. Plug in t, so we have 1 over 1 minus p, and t over here, we have 1 minus p over here, and then minus 1 over 1 minus p. So that's what we have. And if we look at this limit over here, this limit, you have two answers over here. If p is greater than 1, then 1 minus p is negative. And then t to the negative power, if t goes to infinity, it's going to be 0. So the answer over here is going to be 1 over p minus 1. But if p is less than 1, then this goes to infinity. So it does not exist. Limit does not exist. Okay. So what it means is that this integral over here, we say integral from 1 to infinity 1 over x to the power p dx is convergent. That means it has a sum if p is greater than 1. Now, what if p is equal to 1? What if p is equal to 1? And we can just calculate separately. This is a different limit. Limit t is going to infinity, and from 1 to t, 1 over x dx. So we have limit t is going to infinity, and we have log of x and t and 1. So what we have over here is a limit of a logarithmic function, simply log t minus log 1. Log 1 is 0, and we know this is infinity. This is infinity. So that means the limit does not exist. So it also diverges. We say the improper integral diverges. The improper integral diverges. All right, these are the examples for infinite interval improper integral. And we have a different type called infinite value improper integral, and we will do that in a different segment of this lecture.